Okay, guys, this is literally my favorite part of anatomy, the physiology of neurons, how they communicate with each other. And they do that through action potentials. So all throughout this presentation, I really apologize, but I'm going to be geeking out because I think action potentials are some of the coolest things you'll ever come in contact with. So there are a couple things that you need to know before we start talking about the action potential. First is that if an action potential or a nerve impulse, and those two terms can be used interchangeably because an action potential is going to take place for a single neuron, whereas the nerve impulse is all the action potentials taking place in one nerve at one time. So if that action potential starts, then it is propagated over the entire axon. It's an all or nothing thing. If it starts, it goes all the way to the end. If it doesn't start, then nothing happens. So you'll hear the expression all or nothing multiple times. Also, sodium ions are going to rush into their neuron. When that happens, potassium ions are going to rush out of the neuron. This is going to repolarize the membrane, and this will make sense as we go through the different parts of the action potential. And finally, at the end, because we got sodium on the wrong side of the membrane and we've got potassium on the wrong side of the membrane, the sodium-potassium pump restores the original configuration. So this is going to require ATP energy. If you are unfamiliar with some of the biology terms that are going to be used throughout this, you may want to ask because this is going to be very cell biology intense. For instance, an ATP pump or the sodium potassium pump is something that hopefully you learned about with diffusion and osmosis and all that stuff back in biology. If you don't remember that kind of thing, you may wish to review it. So this diagram is one that we will refer to frequently as we travel through the different parts of an action potential. This graph is showing you everything you need to know about an action potential. It starts out by showing you resting potential here at -70. Notice that it's in terms of millivolts. So it's not a lot of electricity, but we're going to be measuring this in terms of electricity. Then a stimulus takes place. Some stimuli are not big enough. When they're not big enough, that's what she said, then nothing happens. This is that all or none. It's not big enough. If the stimulus is large enough to get to threshold, then the action potential is going to take place by having depolarization followed by repolarization. There'll be a refractory period, and then we'll return back to the resting state. Over the course of this entire PowerPoint, we're going to talk about what is taking place in each one of these periods of time. So as we migrate through the graph that we were just looking at on the action potential, we're going to start at resting potential. When neurons are at rest, their membrane potential is -70 millivolts. So what that means is that inside we have a charge of -70 millivolts, which means that there are more negative ions inside the cell and more positive ions outside of the cell. So that -70 is in reference to what's outside the cell. So what's actually happening is we have potassium inside and we have sodium outside. Both have a positive charge, but because there's more sodium outside, there's a higher positive charge outside and a lower positive charge inside, that gives the inside potential a negative charge. So what's going to happen is stimulus is going to take place. And a stimulus, no matter what the stimulus is going to cause a depolarization. So what that means is that sodium ions, which remember we have more sodium outside and we have more potassium inside, so sodium ions are going to move into the cell. That's going to depolarize, so it's going to make the inside less negative. So now we've got more positive inside, so instead of being -70, we're going to increase to, let's say, -60. Now at -60, nothing's going to happen because it's not a large enough signal. We need that threshold to hit -55 millivolts. When that happens, it's going to cause an action potential to take place. Remember, we said it's an all or none thing. So if we get to negative 60, no big deal. The neuron ignores the signal. If we get to negative 65, again, ignored. But as soon as that signal causes a change in the charge between the outside and the inside of the neuron, and it reaches that negative 55 millivolts inside the cell, boom, action potential, all or nothing takes place. And that depolarization continues. Now, it's not as simple as the sodium passes through the membrane, because that phospholipid bilayer does not allow for ions to just pass through it. So in order for the sodium to move from outside of the cell to the inside of the cell, it has to pass through a channel that's in the membrane. When the change in the potential gets to negative 55 millivolts, voltage-gated channels for sodium are going to open up. And these voltage-gated channels are looking out for both the concentration of sodium and the concentration of charges, so looking at that positive versus negative charge. As a result, sodium is going to flow down its electrochemical gradient. So when we break down the electrochemical gradient into two parts, one is the electro part, and that means the concentration of positive ions. Remember that even at negative 55 or negative 70, it doesn't really matter. There's more positive outside, there's less positive inside. So the positive charges going from outside to inside, it's just going down its electrical gradient from high concentration to low concentration. Then we have the chemical part. There's more sodium ions outside than there are inside. So sodium's flowing from high concentration to low concentration. So this part requires no energy. Both the electrical part and the chemical part are going from high concentration to low concentration. So they're moving as we would expect in facilitated diffusion. So coming back to that graph, we have a resting potential of negative 70, and we have threshold set at negative 55. So if there's a stimulus that doesn't hit that potential, nothing happens. Some sodium flows in, and then it gets corrected. But if we hit that negative 55, depolarization takes place. That's where all those sodium channels open up wide and sodium floods into the neuron. As a result of sodium flowing in, we get a positive charge inside the neuron because sodium's positively charged. At some point, sodium's going to stop flowing into the cell because we're running out of sodium ions. This is when potassium starts to flow back out of the cell. Remember, there was a lot of potassium inside the cell to begin with, so that potassium is now going to flow out. This is an attempt to send positive ions outside of the cell, and by sending the positive ions outside of the cell, inside of the cell is going to go back towards a negative internal charge. This potassium pump is slow to start flowing, and then it's also slow to stop. So as a result, too much potassium leaves the cell, and we overshoot that resting potential of negative 70 millivolts, and we end up even further negative, such as a negative 80 or negative 90, which again isn't ideal for the cell. So in depolarization, we saw sodium rushing inside the cell, and that caused our potential at the top to become very positive, which is a far way away from where we started here at resting. Those potassium channels open late, so we get repolarization. Positive ions are flowing out, so that potential, that charge, is coming down, 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 becoming more and more negative. And it accidentally overshoots because those potassium channels are slow. As a result, we dip below negative 70 millivolts. So since those potassium channels are slow to close, too much potassium leaves the cell, and we overshoot that negative 70 millivolts resting potential. We call that portion of the graph where it goes past the resting potential, that overshooting part, hyperpolarization. We've hyperpolarized the cell. So in this part of the graph here, this is where we have overshot and the potassium channels are still open. By the time we get to the trough here of the graph, the potassium channels are finally closed. Sodium and potassium are now on the wrong side of the membrane, but nothing's flowing right now. So this is our hyperpolarization phase. All right, so now we've got two problems. One, we overshot our negative 70 millivolt resting potential, and the other is sodium is on the wrong side and potassium's on the wrong side. Sodium's inside the cell and potassium's outside the cell, but our resting potential had sodium outside the cell and potassium inside the cell. So as a result, a neuron's going to return to resting potential using a sodium-potassium pump. So what's going to happen is 3 sodium are going to be pumped out of the cell and 2 potassium are going to be pumped into the cell. In doing that 3 to 2 ratio, 1 ATP molecule gets broken down because we're pumping things across the membrane. So as a result, we restore a high sodium outside and a high potassium inside, and that is going against that concentration gradient, which is why we need the energy for the pump. During hyperpolarization, and while the sodium-potassium pump is doing its job, there's a refractory period. And that refractory period has 2 parts. The first part is the absolute refractory period. And this is a period of time after an action potential takes place that no matter what happens, there can be absolutely no new action potential. This takes place during repolarization. No matter how big the signal is, no matter how far past threshold it is, the neuron cannot fire again because it's still in the middle of the previous action potential. The next one is a relative refractory period, and this is a period after an action potential when a neuron can fire again, but in order to do so, it's going to need to have a much larger depolarization than normal. So before we said threshold was negative 55. During the relative refractory period, that threshold is going to be much larger in order for the neuron to fire again. This relative refractory period takes place during hyperpolarization. So what happens is this whole idea of the action potential that we've been talking about, we're looking at one little section of the axon where this is taking place. So what happens is while this depolarization takes place at one spot in the axon, it then has to continue that signal all the way down the axon until it reaches the axon terminals. This can be sped up by increasing the axon diameter and by myelin, because instead of it having to go to each adjacent piece of the axon, this signal will jump from one node to the next, making it go much quicker because it can skip large chunks of the axon. Once that depolarization makes it to the end of the axon, we've reached the axon terminal. And so the signal gets converted from electrical, that flow of ions that we saw, the sodium and potassium changing places, to a chemical signal, the neurotransmitters. Neurotransmitters are chemicals that are going to stimulate the next neuron. So impulses from one neuron are conveyed to the next one at the synapse, and the synapse is the gap between 2 neurons. So a neurotransmitter gets released from the axon terminal. The dendrite of the next neuron has a receptor that, when the neurotransmitter comes in contact with the receptor, is going to cause a depolarization of the dendrite. That action potential then gets started for the next neuron because of that signal that's being sent through the dendrites by the neurotransmitter. Okay, so here we have a couple of pictures that are trying to show us what's taking place at the axon terminal. I think they do a pretty good job of that. So step 1, the action potential reaches at the axon terminal. So here we have those synaptic vesicles, all these little green dots are the synaptic vesicles. So what happens is stored inside those vesicles are the neurotransmitters. So that vesicle with the neurotransmitter moves to the axon terminal, the actual end of it, where it fuses with the cell membrane. Those neurotransmitters are then released out into the space between the axon terminal of one neuron and the dendrites of the next neuron. This is called the synaptic cleft or the synapse. It's the gap between two neurons. So the receiving neuron will have receptors. These are proteins embedded in the membrane, and when the right neurotransmitter comes in contact with it, it causes a change. So you can see these, let me actually change color here. These two here are closed because no neurotransmitter has come in contact with it. Whereas the other two, there's a neurotransmitter that has attached to it, and as a result you can see that the channel has opened, and that's going to allow for ions to flow into the cell like sodium ions, and that causes the initial depolarization. So sodium flows down from the outside of the cell to the inside of the cell, causing that depolarization. Over time, what happens is that neurotransmitter gets released by the receptor. It might get broken down, it might not, depending on what neurotransmitter it is, and then it gets taken back up by by the membrane and stored back in synaptic vesicles to be reused. So a little more information on how this synaptic transmission takes place. An action potential is going to reach the axon terminal of the presynaptic cell, so the one that just went through the action potential. This is going to cause calcium channels to open. Again, we're looking at ions. That calcium then flows in, and it's going to bind to proteins that are found on the membrane of the vesicle. That's going to cause the vesicle to come to the membrane, and it's going to spew out all its contents. Those neurotransmitters then move from the presynaptic to the postsynaptic dendrite, where it's going to find the receptor, bind to it, and that's going to cause sodium to flow in, depolarization to take place, and the action potential to now take place in this next neuron. Notice though that this gap here, this synaptic cleft, see how big that gap is? It's actually not that big in real life, but because these chemicals, these neurotransmitters are coming out into that synaptic cleft, while it can stimulate this neuron, it can also go this way and stimulate another neuron, and go this way and stimulate another neuron. So the one neurotransmitter being released by the one neuron can then stimulate multiple different neurons. So I got a little ahead of myself. So the connection is that the release of the neurotransmitter from one cell is going to stimulate not just one, but several other neurons that all meet up in that similar synaptic cleft. If the signal is strong enough, if it meets threshold, then the next neuron, the postsynaptic neuron, will then have an action potential of its own. And that's going to keep the message moving forward. Keep in mind, all of these things are taking place in milliseconds. So for a signal to go from one neuron to the next is happening so fast you can't even measure it. I hope this was helpful, and if not, please ask questions, because this is my favorite topic to talk about. I will gladly chat your ear off about it.